Hey there, and welcome. Today we're diving into a process that honestly sounds like something straight out of science fiction. We're talking about taking a bunch of solid particles and making them flow, splash, and behave just like a liquid.
I mean, really, stop and think about that for a second. What if you could take something totally solid and grainy, like a pile of sand, and get it to pour out of a beaker with the same smooth flow as water? Sounds impossible, right? Well, that's exactly the wild idea we're going to unpack today.
And the scientific name for this bit of magic is fluidization. It's this really cool process where you're not actually changing the particles themselves. Nope, you're changing their environment by pushing a fluid, could be a gas like air, could be a liquid like water, up through them. This upward push forces all the particles to kind of lift up and act like one big, continuous flowing substance.
So here's how we're going to break it all down. First, we'll look at the before state, the starting point. Then we're going to get to the really exciting part, the exact moment the magic happens. After that, we'll see what happens when you push things even further. And finally, we'll check out the tools engineers actually use to predict and control this whole incredible phenomenon.
All right, first things first. Before any of this fluid-like action begins, we start with something called a packed bed.
So picture a big, clear tube just filled with tiny beads. Now, we start pumping some water in from the bottom, but really slowly. At this point, nothing's happening. The beads are just sitting there. But behind the scenes, something important is going on. We're measuring the resistance that the water feels as it tries to squeeze through all the tiny gaps between those beads. And in the world of engineering, that resistance has a name: pressure drop.
And this just makes sense, right? If you want to push more water through that packed bed in the same amount of time, you got to push harder. So as the speed, or velocity, of our fluid goes up, so does that pressure drop. It's a nice, simple, straight-line relationship. But you might want to hang on, because that simple rule is about to get completely broken.
And this, right here, brings us to the most crucial part of the whole story, the dipping point. This is the moment where everything changes, and it's called incipient fluidization.
What you're looking at here is basically a battle of forces. As we increase the fluid's velocity, that upward flow creates a drag force on every single particle, trying to lift it up. And it's fighting against the one thing pulling it down, gravity. And then, bam, we hit that critical point. The upward drag force becomes exactly equal to the downward weight of the particles. The entire bed becomes, in effect, weightless. It's been unlocked, and it's ready to transform.
That exact speed is so important. It gets its own special name, the minimum fluidization velocity. This isn't just a random guess. It's a very specific, calculable number. It is the key that unlocks the door to that fluid-like state.
Okay, and here is where things get really wild. Remember our simple rule, more speed equals more pressure? Well, the second we hit that minimum fluidization velocity, the pressure drop just stops increasing. It hits a flat plateau. How is that even possible? It's because the bed itself starts to expand. It literally makes more room for the fluid to pass through. The system adapts. How cool is that?
Now, to make this a little less abstract, let's look at a real example. For a particular setup with 3 mm particles in a specific liquid, engineers can actually calculate that the magic number, that minimum fluidization velocity, is precisely 36.9 millimeters per second. This isn't guesswork. It's predictable, repeatable science. So we've unlocked the bed. It's floating, but what happens if we keep cranking up the speed? Well, let's jump into our next section and see, because things can go in two very different directions.
So once it's fluidized, the bed can take on two different personalities. On one hand, if you're using a liquid or a gas at a pretty low speed, you get what's called particulate fluidization. The bed just kind of smoothly and uniformly expands. But if you're using a gas and you really start cranking up the velocity, you get bubbling fluidization. And that is a much more chaotic, energetic state, perfect for when you need a ton of mixing.
And honestly, the best way to picture this bubbling fluidization comes straight from the source material. It's described as being similar to gas bubbles in a boiling liquid. Just imagine that. Big pockets of gas are just shooting up through the solid particles, creating this violent, churning motion, exactly like a pot of boiling water. It's an incredible thing to see, and it's that intense action that's so useful in things like chemical reactors.
Okay, so this is all amazing to watch, but how do people actually use it? That brings us to our final section, the engineer's toolkit. How is all this predicted, controlled, and actually put to work in the real world?
So think about it, right? If you're going to use this for some big industrial process, you can't just be winging it. You can't just be guessing what speed you need. You have to know the exact velocity to get your material fluidized. So, how do you figure that out?
Well, you use something like the Ergun equation. Now, we're not going to throw the crazy math at you, but what's important is what this thing does. It's basically a master formula. It takes everything into account: the fluid's density, its viscosity, the particle's size, its shape, you name it. And it lets an engineer calculate that all-important minimum fluidization velocity before they even start building.
And controlling this is absolutely key. Engineers have to operate in a very specific sweet spot. The velocity has to be above that minimum velocity to get the bed flowing, of course, but it also has to be below something called the transport velocity. Go any faster than that, and you basically just blow all of your expensive particles right out of the top of the container.
All right, let's wrap this up. What have we learned? We've seen how a simple upward flow of a fluid can make solid particles act just like a liquid. We learned that the magic really begins at that one critical tipping point, the minimum fluidization velocity. After that point, the flow can be super smooth or it can be wildly chaotic and bubbly. And maybe most importantly, none of this is guesswork. It's all predictable and controllable, thanks to some powerful engineering.
And that leaves us with one last thought. This process is already used everywhere, from making medicines to generating power. So knowing that we have this power, this ability to make solid materials flow on command, what other incredible technologies does this make possible? What problems could we solve next? Something to think about. Thanks for joining me.